So when it comes to this baryon asymmetry problem in the very early universe, this problem that there was apparently more matter created than antimatter, the way I deal with that problem in my quantum gravity model is to deny the existence of antimatter at all. Which seems like quite a radical step forward, I think, or quite a radical move. However, I don't think it's quite so radical, and it really does get back to the sort of the foundational issues which were established in the 1930s with seeking a quantum theory of gravity, and it gets back into the kind of the consequences of the Dirac equation and all these sorts of things, and Dirac's whole conjecture, this idea that he initially conceived of antimatter as being a hole in a Dirac sea, which I don't think is such a bad thing necessarily to revisit, since yet like in the back, like what I conceive of is a background of tunneling particles exchanging bosons with one another. So really, via some sort of hole in the background, we might expect that a W plus is being exchanged between two particles, between some bundle of quarks, some hadron or baryon or something like that. And yeah, like those those particles are exchanging W plus minus particles with one another, and the fact of the existence of, say, positrons arises as a result of the fact that an electron at times may absorb too many, well, not too many, but I mean, has a capacity to absorb more than one W plus particle. So you've got an electron which is charged at -1. If you give it a W plus particle, it becomes a neutral particle. If you give it another W plus particle, it then becomes positively charged, right? So that's what would really be going on. It would be, you can imagine this kind of electrons stuffed up with W particles, and it's been given a positive charge as a result of having too many, which is, I guess, well, one sort of way of dealing with the problem, even though it seems a little inelegant. I do grant you that. It doesn't seem like necessarily the absolute right answer, but it's what I think. I think that's what I think about the problem. So yeah, in the very early universe, what we have is this plenum of subatomic particles, electrons, quarks, everything else. And also, in addition to those particles, you also have bosons. So there's this kind of fermion boson fluid or soup, or, plasma, really, I guess, if you like. And these exist for, very, very brief time until the epoch of nuclear synthesis, and then they all get drawn together via their exchanges of bosons. So really, what we think of as the antimatter component of the early universe isn't actually antimatter at all, but rather it's an underlying plenum or sea of bosons which are yet to be exchanged between the fermions in the very early universe. But once those boson exchanges between fermions begins to start happening, then we find that atomic nuclei get drawn together by those forces. Likewise, electrons get bound ultimately around those atomic nuclei by those same forces, which are ultimately electrical forces. But the electrical forces decompose at a quantum scale to things like the electroweak force and things like that. So we get the exchanges of electroweak particles, W plus and minus particles, and Z particles. Well, that's more like for neutrino exchanges and so on, at the very early stages of the universe, and that's what's been happening.